Hello friends, today we'll solve the analog circuit problems of GATE 2025 Electronics and Communication paper. So this is the first problem. So here a simplified small signal equivalent circuit of BJT based amplifier is given and we need to find a small signal voltage gain. So you can see it's a common emitter amplifier, single stage common emitter amplifier, and we need to find V out upon V source, which is the voltage gain of this amplifier. So in order to do this, we need to apply just KVL or KCL on input side and one time on output side. So on input side you can see that this IB is Vs minus 0 divided by these two series resistance, which is Rs and Rpi. Okay, so this is the value of IB, and on output side if we apply KVL, then V out is what? V out is this current is beta IB, so this current will be also beta IB, so the voltage drop here will be beta IB RL. So V out has opposite polarity of this voltage drop, so it will be minus beta IB RL, and value of IB is Vs upon Rs plus Rpi. So V out is equal to beta minus beta Vs RL Rs upon Rpi. So V out upon Vs will be basically minus beta RL Rs upon Rpi, so which is like this option. So we just need to apply KVL and KCL on input and output loops, and it's done. Okay. So this is second question. Here there is a ideal BJT amplifier, ideal BJT circuit given below, which is biased in active region. The beta is given 100, so an IB value is also given, so we need to find this voltage. Okay, so since beta is given, okay, so we can find first of all IC. IC is beta IB. Now when a transistor is in active region, we can use this relation. So this is beta IB is 10 micro, and then it's like 100, so which is basically 10 raised to power minus 3, so which is 1 milliampere. So IC is basically 1 milliampere. Okay, this current is 1 milliampere, and IE will be basically sum of IC and IB. But since beta is 100, so we can basically ignore IB as almost equal to 0 because it is 100 times smaller than IC. Okay, so we can assume that IC is almost equal to IE, and therefore this part is also 1 milliampere and this part is also throughout 1 milliampere. So voltage drop here is 3 volt. Okay, and voltage drop here is 5 volt, so remaining voltage will be around 2 volt. So if we see the options, then 1.92 is the closest, so we can also do it like that. Or what we can, if you want to do exact analysis, then IE will be equal to IB plus IC. IB is 10 micro is basically 0.01 milliampere and IC is 1 milliampere, so IE is 1.01 milliampere. Okay, so and then if we do this calculation, then we will find out that VC is basically 10 minus the voltage drop here will be slightly more, 5.05, and then it's plus 3, so that will be like almost equal to 1.95 volt. So that's second question. Third question and fourth question are like theory based questions. So it is about ideal op amp. So ideal op amp has infinite input resistance. It is true because when we assume op amp is ideal, then we assume that no current enter into this input ports, plus and minus ports, so both current are zero because we assume it has infinite input resistance. Infinite output resistance is false because current can go inside the op amp. In fact, R out is 0 for an ideal op amp. Okay, so second statement is false. And it has infinite open loop differential gain. So yes, differential gain is basically the amplifier in open loop configuration. What it does is it takes the difference of the two signal and then it amplifies it. Okay, so V out is basically open loop gate time V plus minus V minus signal. So it has infinite open loop differential gain. This is true. Fourth is it has infinite open loop common mode gain. So this is not true. Common mode gain of a ideal op amp is basically 0. Okay, so both the signals are same, then this part will be same, V plus and V minus will be same, so the V out will be 0. So open loop common mode gain of an ideal op amp is 0. So only A and C are true. Okay, another is about ideal MOSFET. single stage DC coupled single stage amplifier having finite load. Common gate amplifier has infinite input resistance, so this is not true, because if the for a common gate amplifier what we do is we give the input at source and take output at drain. Okay, and when we look into the source, then you know that the Rn we usually see is 1 upon Gn. Okay, if this channel length modulation, here it is used ideal MOSFET, so channel length modulation will be ignored, so R out is infinite, so in that case it will be 1 upon Gm. Otherwise it will be like 1 upon Gm parallel to R out. So common gate amplifier has in fact 1 upon Gm is a very low value, so around few hundreds of ohm, so it has a very low input resistance, so it is a false statement. Common source amplifier has infinite input resistance. Yes, common source amplifier input is given at gate, so gate cannot draw any current at low frequency, so Rin is basically infinite, so this is true. Input and output voltage of the common source amplifier are in phase. So common source के अंदर क्या होता है कि input and output in common source amplifier in MOSFET in common emitter, the input and output are 180 degree out of phase, so this is false. Input and output common drain amplifier in phase. Common drain and common gate both have input and output in phase, but common source does not have in phase, so this part is true, this part is false. Okay, now we need to do a question on filter. Okay, active filter. So here it is all the component of band pass filter are given below. So it's given there band pass filter, the lower minus 3 dB frequency is given, upper minus 3 dB frequency क्या होगी ये बताना अपने को. So if you know, it's a standard inverting band pass filter. Okay, so here we can see directly that it is for that this part will correspond to lower frequency and this feedback part will correspond to higher frequency. So F high is basically 2 pi, this part R feedback and C feedback, and this part will correspond to lower feedback R1 and C1. Okay, so this is like R1 is R and C1 is 10C. So if you put it, then it's like 1 upon 20 pi RC. Okay, 1 upon 20 pi RC, and this value is like 1 megahertz, so 1 upon RC is 20 pi megahertz. Now similarly if we do here, then F high is like basically, if you put this value, then F high is basically 20 and 10 upon 4 pi into 1 by RC, and 1 by RC we have found out it's 20 pi megahertz, so basically F high is 50 megahertz. Okay, you can do it through this part also, or you can, if you want, then if you want detailed analysis of this thing, then what you can do is you can find a transfer function. Okay, so this is like a inverting amplifier, so here this will be Z1 plus Z2, which is R plus 1 upon J omega 10C. So if you solve it, you get 10 SCR plus 1 upon 10 SC, and similarly here if you find the equivalent impedance, then it will be Z1 parallel to Z2. Okay, Z1 Z2 Z1 upon Z2, and if you put these values and solve it, then you get 20R 2 SCR upon 10. Okay, so basically V out upon Vs will be, in this case what it will be, it will be minus of Z feedback, this part, upon Z part. Okay, so if you do it, then it will be Z feedback is this part 20R upon 2 SCR plus 10, and then into this part, and when we simplify it, then basically we get this thing. Okay, 200 SCR upon 2 SCR plus 10 and 10 SCR plus 1. So now we want pole, so first pole will be at S is equal to minus 10 upon 2 CR, so minus 5 upon RC is first pole, and here second pole will be at S is equal to minus 1 upon 10 RC, so plus 0.1 RC. So this is the plus 0.1 RC pole, this is the 5 upon RC pole. So this is the dominant pole, and this part they have given it that 0.1 RC is equal to 1 megahertz. Okay, so this gives RC is equal to 0.1 upon 1. So what will be 5 by RC? 5 by RC will be 5 upon 1 into this part, and when we solve it, we can get 50 megahertz. So there are two ways of solving this problem. Okay, so this was the filter part. Just give me a minute. Another question is on this part, which is your differential amplifier. Okay, so what is it? It is the ideal MOSFET M1 and M2 in the circuit are ideal and biased in the saturation region. M1 and M2 have transconductance for 5 millisiemens, and input signals are like V1 is equal to 2.5 plus this part, and this is V2 is 2.5 minus this part. So we need to find output signal V3. So this part is like DC bias part, and this part is the AC source part. Okay, now to solve this we need to do both DC and AC analysis. Okay, so when we do the DC analysis, so what will happen? VD is 5 volt. Okay, so this we will only take the DC input, so 2.5 and 2.5, and this is 2. So you can see that the current will divide into 1 milliampere and 1 milliampere. Why? Because both sides are exactly symmetric, so current will divide equally. So this 1 milliampere is coming to this side, so 1 milliampere will make a drop of 1 volt here, so this part is 4 volt. Okay, similarly this part is also 4 volt. So the basically, so V3 has DC value of 4 volt. Okay, and when we do the AC analysis, then we can see something that both the inputs are VD and minus VD, because one part is like minus plus 0.01 sin omega t, and another part is minus 0.01 sin omega t. Okay, so in such case, in differential amplifier we can use any point on line of symmetry is at 0 volt. So both all this point is at 0 volt. Okay, so we can make it ground, and once you assume it as ground using half circuit analysis concept, so now this is basically a simple common source amplifier, so with voltage gain minus GM upon RD. So GM is 5 millisiemens and RD is 1 kilo, so basically the voltage gain will be minus 5 times the input, so V3 AC output will be minus 0.05 sin omega t. So overall output will be 4 minus 0.05 sin omega t. Okay. Another question is like on this Zener diode plus BJT circuit. So here you can see that ideal transistors Q1 and Q2 are given, and both are biased in active. Okay, so this is clearly inactive, this is also said to be inactive, and beta is 120, and Zener diode is in breakdown. VZ is 5 volt and IZ is also given. IL, this part is given, so basically this is IC part of the collect. Q1 is also given, and this part is this voltage also given. So we need to find the value of R1 and R2. Okay, so let's see how to proceed. So you can see that if we start from here, so this part is like plus minus, and VEB2 is 0.7 volt, so basically this part is 19.3 volt. Okay, and Zener diode voltage is also given to be 5 volt. Okay, and current is also given, so this voltage will be 14.3 volt. Okay, and this current is 25 milliampere. So this thing is done, this thing is done, this thing is done, this part is done, this part is done, and this part is like 12 IL is basically IC of Q1, it is 12 milliampere. So now we can find IB of Q1. How do we find it? Beta IB is IC, IC is beta times IB, so IB is IC times beta, so 12 milliampere upon 120 is basically 0.1 milliampere. So this current is also known, this current is like 0.1 milliampere, so this is 0.1, this is 25, so this part is 25.1 milliampere. Okay, so this voltage is known, this current is known, so R1 is basically V1 upon I. So V1 is what? 14.3 volt, and what is I1? It is 25.1 milliampere. So when we divide it, we get the value of R1 is 0.6 kilo ohm. Okay, which is basically only in option 1. Only in option 1 it is 0.6, in all others, so we know there is no need to find R2, but still if you need to find it, then you can see that this is IE. IE will be basically IC plus IB. IC is like 12 milliampere and IB is 0.1. So this current is basically 12.1 milliampere. Okay, and this voltage will be this part is 14.3 and this is 0.7 voltage rise, so this is 15 volts. So basically R2 will be again same V upon I concept, so 5 volt drop and 12.1 milliampere current flowing through R2, so R2 is 0.4 kilo. Okay, that's why again option number 1. Now we need to do the last question, which is on diode. Actually there is one more question. Okay, so this part is on diode is like which of the following plot is VI swept from minus M to M. So there are two plots. First is of V out upon VA, and another is I1 upon VA. Okay, so when VI is positive, then diode will battery will push current like this, and this diode will help it. 1 and 2 diode will help it, and current will flow like this. Okay, so it is simply like simple, all the voltage will come across this resistor, so V out will be plus M. When input is plus M, V out will also be plus M. So this part is linear. Now when, and in this sense the current will also be M by R only. Okay, so there is no issue about it. So this part is also clear, this part is also clear, this part is also clear. Okay, this part is wrong, M by R. Then when Vi will be equal to minus M, then what will happen? So when Vi is equal to minus M, then also you can see that current will flow through in this way. Okay, so direction of current will be opposite, but voltage drop will be positive. Okay, so voltage drop polarity will be same. Even when Vi is minus M, we will get output as plus M only. Okay, so this part will be correct, this part will be wrong, because when Vi is equal to minus M, then output will be not equal to minus M, it will be equal to still plus M only, because even when current flows like this, so V out polarity and value of current is not changing, so V out will be still plus M. And but when the polarity is changed, say Vi is like this, then current will flow in this way. Okay, so this current direction will be M by R. Okay, this voltage upon this resistance R. So in this direction it will be I1 is equal to minus M by R. Okay, so this time the direction of current is opposite, so it will be minus M by R, this part. Okay, and this drop will be like, suppose this is 1, this is A and this is B, so this will be basically VA minus VB. So VA is at plus M part and VB is at ground, so V out is equal to plus M only. So this part and this, both these curves are true. Okay, so it's a polarity based confusing question. One more question is there on diode. Last question. It's like this, that the diode in the circuit shown below is ideal when input voltage is like 10 sin 100 pi t. So time duration for which the diode is forward biased during one period. Okay, so we need to find the time duration for which the diode is forward biased. So first of all, what we will do is we will find out when the diode is on. Okay, since the voltage is swinging, so when the diode is on, so for that we will first find the open circuit. First we will find the VOC by assuming diode is off. So let's say diode is off. Okay, so VOC will be was VP minus VN. So VP is basically, when the diode is off, it is VI, and then this minus of this voltage, which is minus 5. So basically VI plus 5 is VOC, and for diode to be on, VOC must be greater than 0, so which basically means VI plus 5 should be greater than 0, which means VI should be greater than minus 5. Now what is VI? VI is basically 10 sin theta. Okay, this thing is theta. It should be greater than minus 5, which means sin theta should be greater than minus 0.5. So sin theta, whenever so if you draw the sine curve, then sin theta is always greater than minus 0.5 to this part and up to this part. So here after like 180 and then 30 degree, if you move more, because 30 degree 1 by 2 value cross कर जाता है sin की curve. So from 210 to 330, okay, this is 360 degree. So this part is the part where the diode is off. Okay, so diode is on for like 240 degrees. If we count all these degrees, and is 240 degree, and 240 is basically 2 by third. 2/3 of the time the diode is on, so T on is basically 2 by 3t. Now the time period can be easily found because omega is 2 pi f, which is f is 1 by t, so 2 pi t, so t is basically 2 pi by omega. So we put 2 pi by omega, 2 by 3 into 2 pi by omega. What is omega? Omega is here 100 pi, so when we cancel it we get it. And since we need to find the time in millisecond, we need to multiply by 1000 also, so when we solve it we get 13.33 millisecond. Okay, so these were all 9 questions. Thank you.